So what I wanted to think about then, so that's in relation to the electrons and how they can be lost or gained. Now, if we think about then the neutrons then, okay, so the neutrons are present here within the nucleus of the atom as well. So what we have is, so the number of neutrons. So how do we figure out the number of neutrons? So the number of neutrons is actually the mass number. So if we take this number here, and I've just rounded it up to 16, so it's 5.999, but I've just rounded it to 16. And if we subtract the atomic number from it, okay, so it's the mass number minus the atomic number. That's how we figure out the number of neutrons that are present within the nucleus of the atom. So it's going to be 16 minus 8, which is equal to 8. So in the case of oxygen, oxygen has 8 neutrons in the nucleus of the atom. So if we have a look here, so we've 1, 2, 3, 4, 5, 6, 7, 8. We've 8 protons and then we've 8 neutrons. Now the neutrons are negatively charged, so they don't actually, the neutrons, there's no charge on the neutrons. They don't carry any charge at all. Now the number of neutrons that are present within the nucleus of an atom can actually change. So you can get, so this particular model that we're looking at of oxygen has 8 neutrons within its nucleus, but you can also get atoms of oxygen that have different numbers of neutrons, and they will have slightly different masses as well. Now, the reason why when you look in the periodic table and you see that the mass number, it's not a whole number, it's because what they do is within nature, if you were to take a sample of oxygen, you'll have and you were to look at all those individual atoms that make up that sample of oxygen, they will all have different numbers of neutrons within the nucleus of their atoms. And what they do is, these are what are known as isotopes. So you can have an atom of oxygen, one that has 8 neutrons, and then you can have another oxygen atom that has 9 neutrons. Both oxygen atoms will have 8 protons because that's what makes it an oxygen atom, but they can have different numbers of neutrons, and these are what are known as isotopes, and we'll talk a little bit more about those later on in a different lesson, but it's just to kind of give you a general overview. So what they do is, when they take a sample of oxygen, they measure the mass of all the different types of oxygen atoms that are present, and they get an average. And that's why when you look on the periodic table and you look at the mass number, it's not actually a whole number. So then, if we think about, just to go over then what we've talked about. So we look on the periodic table. Okay, so we see here. So if we have a look in here. So we have, for example, the coronavirus. The coronavirus has all of these macromolecules such as proteins. If we look at proteins are made up of amino acids, and then if we actually go right down and look at the structure of what are amino acids made of, they're made of these atoms. So for example, they have atoms of oxygen here, and each atom that makes up the parts that make up, for example, the proteins, they are represented on the periodic table of elements. And that's what the periodic table of elements is all about. So if we look on the periodic table, then we have, for example, oxygen here, which is an atom that makes up the amino acids that makes up proteins, which makes up the part on the coronavirus. So then when we look at the periodic table, and we look, let's say, at one of the individual atoms, we see that it has this number here, which is 8, which represents the atomic number, and this number down here, 15.99, which represents the mass number. And then you also have the symbol that represents, each element has a symbol. So for example, oxygen, the symbol is O. So then, if we look then at what does that actually mean? So we are looking here at oxygen. So oxygen's atomic number is 8. That means that if you were to take an atom of oxygen and you were to look at it, it would look something like this. So the 8 represents, the atomic number represents the number of protons that are within the nucleus, and we see that it has 8 protons within the nucleus. The protons are positively charged. They carry a charge of +1. So you have 8 positive charges inside the nucleus. Then you have 8 also represents the number of electrons that are present within an oxygen atom as well. So in this case, you have 8 electrons. So you have these electrons that that move around, and they move around in what are called orbits or shells outside of the atom. The nucleus then contains the protons. Then also as well, within the protons, within the nucleus, you have these other particles that are known as neutrons. Now, the protons, neutrons, and electrons are what are known as subatomic particles. So subatomic particles. So that means that they are the parts that make up an oxygen atom. So you have subatomic. So subatomic. Okay, so the subatomic particles are the protons, and neutrons, and electrons. If you want to work out, so that's how you figure out the number. So if you want to know like how many protons are present and electrons are present within an atom, you look at the periodic table, look at the atomic number. In the case of oxygen here, we have 8 protons and 8 electrons. Now, we have this mass number as well. So the mass of an atom, it comes from the protons and the neutrons. So protons and neutrons, they both carry a mass of 1. So the mass number is represented here. Now we can round this up to an even number, so 16. So what we know is that the mass of the nucleus of an oxygen atom is 16. So that means that it has 8 protons, but it also has 8 neutrons as well present. Now, if you want to figure out the number of neutrons that are present within an atom of a particular element, what we do is so the number of neutrons is going to be equal to the mass number, which is the number that's here, minus the atomic number, and that will tell us the number of neutrons that are present. So we see here in the example with oxygen, we have a mass number of 16 minus the atomic number, which is 8. So that means that we have 8 neutrons within the nucleus of the atom. Neutrons are neutral, they don't carry any charge. Also as well, we talked about, so if you have, for example, in the case of oxygen, you have 8 protons, that means you have 8 positive charges. And you've also got 8 electrons, so that means you have 8 negative charges. So the number of charges, they cancel each other out. So their overall charge on an atom, for example, is neutral, it's 0. Okay, because you have an equal number of positive charges from the protons and an equal number of negative charges from the electrons. Now, scientists also, they like to be able to represent elements and look at them and talk about them. So they like to use different types of models. So one model is what's known as the Bohr model. So it's B-O-H-R model. So it's called the Bohr model. So the Bohr model is just really a representation or a way that we can represent and look at atoms. So what you do is first of all, you create a circle. Okay, and this circle represents the nucleus of the atom. Okay, so it represents the nucleus of the atom. So this is going to be the nucleus. And then what you do is you split this in half. Okay, and the left hand side represents the protons and the right hand side represents the neutrons. So if we take the case of oxygen, for example, so we know that its atomic number is 8, so the number of protons is 8. So we just represent that by writing an 8 and a P beside it. Okay, so that means that within the nucleus of an oxygen atom you have 8 protons. And also then as well, you can write the number of neutrons that are present. So we have 8 neutrons. Okay, so 8n. So what this is just represents the number of protons and the number of neutrons that are present within the nucleus of the atom. The next thing that you want to represent now on your Bohr model is what's known as these orbitals or shells. So if we have a look here at oxygen, for example, we can see here that oxygen, so there's a shell or a space where the electrons can move around. Okay, so you have the first shell and it contains 2 electrons. Then you have the second shell. So you can represent these as shells within on your Bohr's model. So you can just draw like the first shell. Okay, so this is the first shell, and these are the electrons that are closest to the nucleus. So the first shell will contain, it can hold 2 electrons. Okay, so the first shell always holds 2 electrons. So we can write it like this. And then we have the second shell, which is something like this. And the second shell, so we've used up 2 of the electrons. We know that we have 8. The second shell can hold up to 8 electrons. So we just represent those on, so we can represent just 8 of them. So 1, 2, 3, 4, 5, 6, 7, and 8. So each of these lines represents what's known as an orbit. Okay, and then these guys here are known as electrons. So basically all it is it's just a way to represent the atom. So this is oxygen. And it shows us the arrangement of the subatomic particles. So you have the protons and neutrons in the middle, and then you have the electrons in the orbits around the nucleus of the atom. So really what then, like a way to kind of think about this is then that when you take, for example, like when we look here at the coronavirus, and you look at the coronavirus can be broken down into parts. So each part then, for example, these spikes here are made of, part of the spikes are made of proteins. And then when we look at proteins, part of proteins, they're made up of all these different elements that are all joined together in particular ways. And then when we focus on one of the elements, for example, oxygen, we can see that it can further be broken down then into, the atom can be further broken down into all of these, what are known as subatomic particles. So they have protons, neutrons, and electrons all joined together, and they're arranged like this. So you can see that as you like, if you think about how complex this like piece of the coronavirus actually is, and it can be broken down into these atoms, and these atoms are extremely small. So just to give you an idea of how small an atom is, if you take, let's say, just this full stop here, so okay, so you have that full stop that I've just written here. Now, the number of atoms that are contained within that full stop is a huge number. Okay, you'd be talking on the magnitude of, if you think about all the grains of sand on all the beaches on the planet. So think about all of those individual grains of sand on all the beaches on all the planet. That's how many atoms would fit on that space that I've put on the screen there in front of you. So these atoms are extremely small, but again they're kind of like a system, like the overall system of the coronavirus, and they have a very specific structure, and we understand the structure of the atom, and we understand the parts of the atom and how they're arranged. So we have in the middle you have the protons and neutrons, and then on the outside you have these electrons as well. Now, so these like elements, so each of these elements within the periodic table can be represented like this. Okay, and then you can use, for example, this thing that we call the Bohr model to just represent like the way that the atoms are made, the way the atoms are arranged. Now, if you think about when you look at the like when you look at the atom, okay, the majority of the atom is just this empty space. So nearly over 97% of the atom is just this, what we call empty space. The rest of it then is made up of these subatomic particles. Now the mass then, the mass of an atom comes from the nucleus, and it comes from these subatomic particles, protons and neutrons. So it's just to kind of give you an appreciation then for like how complex even the simplest part of a molecule that makes up part of the coronavirus actually is. It's very complex. Now, what we'll do is we'll spend a little bit more time just looking at the arrangement, like what the atom like. So this is like the fundamental part of what's called matter. So matter basically is anything that can occupy space and has volume. So for example, the coronavirus, it occupies space, okay, and it also it has mass and it occupies space. So if you think about the mass of a coronavirus, okay, so the mass comes from all of the atoms that make up the coronavirus. Okay, so you think about like the staggering number of atoms that are actually going to be arranged to make up all these macromolecules, and then those macromolecules then make up all of the individual parts of the coronavirus as well. So it's an absolutely huge amount of atoms that are arranged in many different ways to give you this thing that we call the coronavirus. And the mass of the coronavirus comes from all of the masses of all the protons from all the atoms that make up the coronavirus, all the protons and the neutrons. Now, if we have a look then, what's very important then as well is these electrons. So the electrons are like the glue that actually hold individual atoms together. So if we have a look here, and I'm going to talk about that a little bit more in the next lesson. So if we have a look here, for example, we can see that we have an oxygen atom like connected to a carbon here, okay? And what happens is like the electrons that are within the carbon, they overlap with the electrons that are in the oxygen and they join together. So that's why it's really important that scientists understand, for example, they understand number one, the arrangement of like the way these subatomic particles are arranged, but then they also understand that how, like let's say we have one atom here, if we have another atom beside it, well, like what is it that keeps them connected together? And it's these electrons that keep atoms all connected together and they give it its structure. And that's what we'll talk about. We'll talk a little bit about that in the next lesson. We will look at like how atoms actually join together, and we have these what are known as chemical bonds. Okay, so just for today, I just really want you to understand like the structure of the atom and how the periodic table relates to the structure of the atom, and then how atoms relate to the structure, for example, of the coronavirus. Okay, thank you for listening.